Okay. Although we simply denote the differential by df, but you need to know that df depends on h and also depends on a, because for different a, this lambda will be different. Okay, so df actually depends on a and h, but for every given a, it depends on h linearly. I will have a remark. df depends on a and h. For fixed a, df depends on h linearly. That is, df is lambda h. Or if you want, you can also write df h. Okay. This is a simple remark, but we will not use this later. So for a function defined near a, which means it is defined at least in an R neighborhood of A, right? We have three concepts. The first is continuity. Is f continuous at A? This is a property. The second is that the partial derivative of f at A. Okay. The third is f is differentiable. We just introduced the differentiability, right? So these are three basic topics about a function defined near the point A. So what's the relation between these three properties? Okay, their relation can be described in the next theorem. If our function is differentiable at the point A, then the first thing is that f is continuous at the point A. The second thing is that for any I, the partial derivative of f with respect to xi, we denoted by difa, exists. And we not only know that it exists, we also know that the value of the partial derivative is exactly the lambda I. We have seen that the differentiability involves a vector lambda in Rn. Here lambda I is the ith component of lambda. Okay, so for every I, the partial derivative equals lambda I, which means the gradient of f at A is nothing but lambda. Okay, so this is a very important theorem about the relation of these three concepts we just record. Okay, so differentiability is the strongest assumption because it implies the continuity and the existence of partial derivative. Okay, so the proof of this theorem is also very easy. First, we prove that f is continuous. So f is differentiable at A means that fa plus h minus fa is lambda, the inner product of lambda and h plus the norm of h. Therefore, this equality holds as h goes to 0, as the norm of h goes to 0. These are equivalent. H goes to 0 is the same as the norm of h goes to 0. Okay, so by differentiability, or since f is differentiable at a, so there exists such an h lambda, such that this red equality hold. Lambda is an element in Rn. So limit h goes to 0, fa plus h minus fa will be the limit of h goes to 0, lambda h plus this. But obviously, this is the limit of this of the higher order term is 0, and the limit of lambda, the inner product of lambda and h is also 0, because the absolute value of the inner product by Cauchy-Schwarz inequality, this will not greater than the norm of lambda multiplied the norm of h. But h goes to 0, therefore the right hand side goes to 0. So in other words, the right hand side of our this equality will be 0. So when h goes to 0, fa plus h minus fa, the limit of fa plus h minus fa is 0. This means h goes to 0, fa plus h is nothing but fa. These are equivalent. Or you can write in other way, y goes to a, or maybe x goes to a, fx is fa. So this means that f is continuous at a. Therefore, this proves our first conclusion of our theorem. Okay. Next, we prove that the partial derivatives exist, and the value of the partial derivative is lambda I. Okay. So the second result, again, f is differentiable at a, which means as h goes to 0, fa plus h minus fa is lambda and then h higher order term. Okay. Now we want to show that this is lambda I. We want to show that the partial derivative of f at a exists and equals lambda I. Recall that the partial derivative of this, by definition, this is t goes to 0, fa plus tei minus fa divided by t. Okay, this is the definition of a partial derivative. Okay, so compare the definition of partial derivative and this differentiability. Compare these two. You should be able to find that set h tei. So you consider h to be tei in the definition of differentiability. We see that fa plus tei minus fa will be the inner product of lambda and the tei plus. So ei, what's ei? Ei is the 0, 1, 0. So tei is 0, t, 0. So h goes to 0 is equivalent to t goes to 0. So the higher order term of h is the t. Maybe I can explain this in another way. Okay. No. Because h is ti, you see the norm of h. The norm of h is t. Therefore, the higher order term of the norm of h is t. Okay. So the limit t goes to 0, fa plus tei minus fa divided by t, which is the inner product of lambda and ei. Maybe I write one more step. Inner product of lambda and tei plus t. But the inner product of lambda and tei here is t multiply the inner product of lambda and ei. But the inner product of lambda and ei is exactly lambda I. So the first term here on the right hand side is t lambda I, but you divide it by t, therefore only lambda I remains. On the other hand, this part goes to 0 as t goes to 0. So in conclusion, the right hand side, the limit of the right hand side is lambda I. Okay, so this means that this limit exists and equal lambda I. So this proves that the partial derivative of f at a is the limit on the right hand side is nothing but lambda I. So this proves that partial derivative exists and equals lambda I. Or equivalently, this means that the gradient of f at a is nothing, is exactly the lambda in the differentiability. Okay, so this proves this important theorem. So this theorem means that the differentiability implies continuity and the existence of partial derivatives. How about the reverse of this conclusion? I will show you by example that the reverse is not true, by a very simple example.